Hi there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be going over a second part of addition reactions, and I'll link the previous video down below. We've also started doing a podcast format for those who'd like to reinforce the concepts on the go, and I'll link those down below. So let's start with the epoxidation opening with an acid. And an epoxide is a three-membered cyclic ether. They're usually stable unless they're put in an acidic solution, so that's when the magic happens. The first step is the protonation of the epoxide by a proton. The second step is an SN2-like reaction where the backside attack happens by water to break open the ring. And note that because we have a backside attack, the stereochemistry that we'll observe is an anti-addition. The last step is the deprotonation of the water to form the diol and the anti-conformation. You'll often see this product being referred to as a glycol, which is essentially another term for a diol, which is two alcohols. And with that, you now have a alcohol in the anti-conformation. Now the next step, or the next reaction, is the halogenation of alkenes. Shown is the general reaction of a halogenation. In the first step, the halogen attacks the double bond and then forms what's called a halonium ion. Now the halonium ion is a three-membered ring and it has a lot of ring strain. That plus the positive charge on the halogen makes it a perfect candidate for being an electrophile. The second step is the opening of the ring by the halide. The halide attacks in another SN2-like fashion, which is a backside attack. And then again, note because there is a backside attack, the stereochemistry that we will see is anti-addition. And with that, we'll also get the enantiomer of the other product. The next reaction is the Halohydrin Formation, and it is very similar to the halogenation of alkenes with one slight difference. So again, in the first step, the halogen attacks the double bond and forms what's called a halonium ion. The second step is the opening of the ring by the water. The water attacks again in an SN2-like fashion, which is the backside attack. Now, the reason why the water attacks over the halogen is because water is being the solvent, and with the halonium ion being very reactive because of the ring strain, it will react with anything. And since there's an abundance of water due to it being a solvent, it will attack it first. Now, again, because there's a backside attack, the stereochemistry that we will see is the anti-addition. The last step is the deprotonation of the water, giving the product of the halohydrin plus the enantiomer. Note that in the case where we don't have symmetrical alkene, the water would attack the carbon that is more substituted with the hydrogens. The next reaction is the hydrogen halide addition to alkenes. Again, this is what a general reaction looks like for a hydrogen halide addition. The first step is the double bond being protonated, which then turns into a carbocation. Now, as we remember before, when we want to have the carbocation on the more substituted carbon because of its stability. Now, another note also is that because the carbocation forms, rearrangement is possible. Because of this, we know that the proton is added to the carbon atom with more hydrogen substituents, which is the Markovnikov rule. Now, the last step is the halide attacks the carbocation to form the product. Now, let's move back to the rearrangement possibility for a second. So if we look at this example and we go through the first step of protonating the double bond, we see initially that we have a secondary carbocation, which is this right here. However, after a hydride shift, we make it into a tertiary carbocation, which is more stable. And then the second step is when the halide attacks to form the product. And as you can see right there, that we have a tertiary chloride. As always, you always want to remember to be on the lookout for the possibility of rearrangements whenever a carbocation forms. Now the next reaction that we have is the hydroboration of alkenes. Now we've explored a way to make an alcohol from an alkene with the Markovnikov addition. An example of that would be the hydration reaction. However, there is another way to form an alcohol in the anti-Markovnikov addition. Now, if we have an alkene and use borane, which is BH3 and peroxide, we have the anti-Markovnikov addition of the OH group onto the alkene. Now, if we look at the first step, the double bond attacks boron, and also a hydride shift occurs at the same time. Now, you want to take note that the boron bonds to the carbon that is least substituted with the alkyl groups. Boron is relatively bigger compared to hydrogen, and if you remember the concept of steric hindrance, it would naturally bond towards something with less steric hindrance, which is what we observe. We also see a syn addition, and that's because in the first step we mentioned that the double bond attacks the boron and the hydride shift happens at the same time. Now because of that, the addition of the borane and the hydrogen must be on the same side of the plane. Now the last step is oxidizing the boron and with peroxide to replace the boron with the hydroxy group. Now the last reaction that we have is Oxymercuration-Demercuration. Now Oxymercuration-Demercuration is another way to convert an alkane to an alcohol without rearrangement. Now due to the formation of the mercurium ion, no carbocation is formed and thus no rearrangement can occur. Now with the oxymercuration part, the double bond attacks the positively charged mercury and forms a mercurium ion. Now much like the other examples, this is a three-membered ring with a lot of ring strain, and it is very reactive. Now the second step is when the water opens up the mercurium ion and is followed by a deprotonation, which is this right here. The demercuration part is defined as the removal of the mercury attached to the chain. So that is the final step when we use sodium borohydride, which is NaBH4, which is a reducing agent, and then it helps remove the mercury and replaces it with a hydrogen atom. Now, one thing to note is that the oxymercuration-demercuration will give the Markovnikov orientation. Now, during the second step, where the water opens up, the mercurium ion, it will attack the more substituted carbon because it stabilizes the positive charge better. With that, that concludes the video. Hit that like button, the subscribe button to support the channel, and share it with your friends who need help with organic chemistry. In the next video, we'll be putting up all the addition reactions into one spot and helping you decipher which is best to use when you start synthesizing reactions. I'll be putting up more videos, so comment down below what you'd like to see. Social media links are down below, and as always, remember, you gotta go.